Welcome to Chapter 5, Lesson 6, and Lesson 7. We're going to cover this in about 2 days. The exponential and log equations that you saw before break, or before these lessons, are used to describe a particular type of rapid growth and decay. COVID-19 is now flattening in this type of model, but it used to be growing, and actually it goes through periods of both growth and decay, depending on the season. All the self-isolating efforts are to slow that spread and flatten out the curve, but we're going to look at growth that doubles. So, for example, if you have one piece of paper and you put it down, that's not very thick. And then if you have 2 more pieces of paper, putting it down on top of that, then it's still not very thick, but it's a little bit thicker than it used to be. If we keep doubling, then if we add double the previous amount, so adding 2 pieces after the first one, then 4, then 8, then 16, we're following an exponential model, y equals 2 to the power of x, where y is the total number of sheets of paper in my stack, and x is the number of times that I have doubled my pile. So to find out how many pieces of paper there will be in the pile on the 10th time that you find it, you double your 2 to the 10th power, or you find your 2 to the 10th power. And again, if we check here, 2 to the power of 10, you would have about 1,024 pieces of paper if you put down 1, then 2, then 4, then 8. Let's see here. 1, 2, 4, 8. And then 16, 32, 64, 128, 256, and 512. So adding all of those together. So most people don't actually think exponentially. So if, the brain actually has a very difficult time predicting this kind of rapid and huge growth. So think about it this way. Paper, very, very thin. The distance to the moon is about 250,000 miles. There are 5,280 feet in a mile and 12 inches in a foot. So one piece of paper is about 1/256th of an inch. So if I have 250,000 miles times 5,280 feet in a mile times 12 inches in a foot, we're going to get 1.584 E10. Again, that is scientific notation. So 1.584, again, E10 is really just the way the calculator expresses that. We would actually say it's 1.584 times 10 to the 10th power, or 1, and then we move our decimal 10 places to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the distance to the moon is about hundreds, thousands, millions, billions, 15,840,000 inches. Again, a piece of paper is 1/256th of an inch thick, so 256 stacked sheets are an inch. We would get if you multiply that by 12 inches per foot, it would take 3,072 pieces to make a foot. 5,280 feet per mile would get you 16,220,160 pieces of paper stacked up would cover a mile. So suppose you start with a piece of paper and put another piece on top of it. You then put 2 pieces on that, 4 on that, etc. Every time you add as many sheets as there were already in the pile, you double it. So estimate how many times you would need to add paper to the original pile to reach the moon over 250,000 miles away. Go ahead and pause here. See what you can get with this. All right. So we could do this either with the inches that I found out before or with the miles that we talked about here. So if my number of pieces of paper, which are each 1/256th of an inch thick, equals 15,840,000,000, then it would be times 256, 4.05504 times 10 to the 12th. Or again, lights turned off on me. There we go. That would be 4, and then we move our decimal 12 places to the right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We would need hundreds, thousands, millions, billions, 4 trillion pieces of paper in order to get a stack of paper from the ground to the moon, I believe is what that would find out what that would be. But let's see. That we probably could have done this a little bit easier with exponents. So if we use y equals 2 to the power of x, x is the number of times we add paper. So again, we came out with the number of pieces of paper that we would need to find: 4 trillion, 55 million, billion, 40 million pieces of paper. So we want to find an x value that gives us that y value. So 2 to the power of x equals 4,055,040, and then 6 more zeros. So we could solve this with logs. So the log of 2 to the x power equals the log of, let's make that 4.05504 times 10 to the 12th power, because that's going to be easier to write over and over and over again. Again, we can take that x and put it out in front as multiplication. So x times the log of 2 equals the log of 4.055 times 10 to the 12th power. And then we'll just divide by the log of 2. So log 4.05504, make sure I get that, times 10 to the power of 12, close parentheses, and we'll divide that by the log of 2. Should be about 41.883. So we would have to double the number of pieces of paper, 41, almost 42 times. But by the time we hit 42, we're actually going to end up beyond the moon. So if the moon would take 4 trillion, 4 trillion pieces of paper to reach there. If we tried x to the 42nd power, or sorry, 2 to the 42nd power, we would get 4.398046511 times 10 to the 12th, or 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We would be a few pieces of paper beyond the moon at that point, because it only takes 4 trillion-ish, but this would be about 4.4 trillion. So you would have almost 40 billion or 30, 35 billion, 39 billion extra pieces of paper going beyond the surface of the moon. Finish up all of this. So we should come up with an answer that's between 41 and 42, since 2 to the 42nd power is already bigger than our target distance. So again, in other words, this 42nd time you add paper, the pile will go past the moon, so don't try it. Also, you probably need to cut down a lot of trees in order to make that happen. Maybe even also compost or recycle every piece of paper that's ever been made. So again, compare the answer with the estimate that you wrote down. Was your estimate too big? If so, that's okay. That's normal. You can reread the bolded comment. Again, most people don't actually think exponentially. The brain has a very difficult time predicting very, very large numbers and growth like this. And also, if you'd like, Mythbusters also looked at this problem one time in how many times can you fold a piece of paper, and once you start folding in half, how thick does it get? Because again, a piece of paper is just one piece of paper thick, but if I fold it once now, it's 2 pieces of paper thick, but if I fold it again, that's 4 pieces thick. Again, you can kind of start counting the edges. 1, 2, 3, 4. If I fold it again, then it's going to be 8. And if I keep going, eventually I would have a very, very, very thin piece of paper that could possibly reach the moon if I'm able to fold this 42 times.